I'm Greg. I'm co-founder, CTO at Undo, and we're going to talk about go green, stay green. So really the principle being you've got your CI or whatever your test suite is, and it's probably not 100% passing and 100% green, and we're going to look at what it takes to do that. But first of all, why you should do that. And I'm going to start with the Austin Powers films, which, if you're familiar with these, are kind of very stupid, puerile humor, lots of sort of silly sexual innuendo and fart jokes and stupid puns, and therefore they're completely awesome. And the kind of premise is that this guy is put to sleep in the 60s, woken up in the 90s, and he doesn't fit into the technology change in that period probably isn't as much as everybody was assuming it would be in the 60s, but when he wakes up in the 90s, he finds that it's the culture fit that is the problem, the culture that's changed. And I think with software development, there's kind of a parallel here, right? I mean, if you put, and I've said 1990, but I think even 1985, if you put a programmer to sleep in 1985 and woke them up in 2005, actually they'd probably not be like Austin Powers. They'd be kind of okay. Everything looks kind of the same, right? So we go from this kind of world, this is like a really early version of Visual Studio or Visual C++ as they called it back then, and you go forward to sort of mid-2000s, and okay, there's some more pixels, right? And things have kind of changed a bit, and sure, the internet's kind of come along, but the way that we develop software hasn't really changed. And if you put a programmer to sleep in 1985 and woke them up in 2005 and sent them to work, they'd pretty quickly get to grips with what's going on, right? I think if you did that same thing then, put someone to sleep, say in the mid-2000s, and woke them up 10 years later, they'd be like Austin Powers in the films. They'd be all at sea. Suddenly everyone's like standing around a whiteboard with sticky notes on it, right? And people are talking about pushing code. You push code to some distributed repository, and then it passes some tests and immediately goes live. And this would be sort of culturally, not just technologically, but culturally a big shock for that programmer, right? So I think actually this mirrors technology development, computing developments, which come in waves. And things kind of settle down, almost actually like in the natural world with evolution. You don't get this kind of slow, continual change. You get what the evolutionary biologists call punctuated equilibrium. Things kind of settle down and then they change quickly. And we've just gone through, I think, over the last sort of 10 years, this very big change. 2005, not that long ago, and if you were doing some kind of continuous integration, it would look like it was happening, but it was rare. You were in the top few percent. In fact, I'd go as far to say, if you were even doing decent automated nightly testing of your repository, you're probably in the top half in 2005, right? Really, we just developed software in a much more kind of ad hoc way, and we did far, far less testing of it. Testing was often some people in the corner who, followed these scripts. Scripts not being like bash scripts or something, scripts being documents, pieces of paper, do this, then do this. Then. I mean, there is still, shockingly, some software is still tested like that, but it's happily now really in the minority. So yeah, it's all changed, right? So we've gone to this kind of agile world, but it's gone more than that. We've gone into this kind of, continuous distribution, continuous deployment world, and with distributed version control and everything else, right? So we know all about this. But I think we're not quite there yet, and I think there's one piece of the puzzle, if you like, that's missing, which is this bit, right? Test. Tests okay, so we deploy. What does it mean for the tests to be okay, right? Does it mean that all of the tests are passing? Because that gets to be a really hard thing to do, right? I mean, does it mean that we have complete test coverage? Well, actually, probably not, right? It's basically impossible to get genuinely 100%. I don't mean just line coverage. I mean covering all the permutations of all the possibilities that there could be. Do you mean that the test suite is 100% reliable? Well, it kind of has to be. If you're going to take green as meaning, yeah, you can deploy, your test suite had better be reliable, right? Now, the context for this, I'm jumping around a little bit, but the context is traditionally we've seen software as this kind of productivity versus quality trade-off, or if you like, velocity of innovation versus quality, right? So if you're writing software for, say, flight control system in an airliner, perhaps that's not a great example in the current sort of news climate, but or in a nuclear power station or something, then you accept a very low rate of innovation on the basis that it is going to be absolute, you're going to make it, sort of as close to perfect as you can possibly do. And if you're writing, some kind of website, you're in competition, velocity becomes more important. And this has been a way that we traditionally kind of looked at software, and another way of viewing this is as a kind of an optimal amount of bugginess for software. You might think naively that we all want the software to be 0 bugs, but actually, there's only so much of a price you'll pay for that in terms of velocity of innovation. But I think one of the things we found with all these changes, the way we do software, agile and CI, CD, and everything else, is that actually it's not quite that trade-off. You can get both. You can get both high quality and high productivity by things like CI and running lots and lots of tests. But only at the point, you only get to this top right, this nice bit of the chart where you're high quality and high productivity, if you have an extensive and reliable test suite. Right? And let's look at what that means. I mean, let's take the old, this old world I was talking about in 2005, where there's some people in a corner who are sort of doing the tests. Maybe you're doing 50 tests once a week, right? And let's say that half of them are completely solid, and so 25 of them always pass. The other half are like 99% reliable. You do some maths, you only get one spurious failure per month, right? You can kind of deal with that. In the modern world, with elastic compute resource and CI and everything, this 50,000 tests an hour is not aggressive. I mean, I'm sure many of us are working in projects where we have more than that, significantly more than that. Let's take that same metric. So half the tests are completely reliable, and the other half, they're 99% reliable. They give you just that 1% sort of spurious failures. You're getting 250 failures an hour, right? Or hundreds of thousands of failures, spurious failures per month. So this world no longer works, right? And even if you push these numbers quite far, let's say we're doing 99% are completely solid, and only 1% fail spuriously 1% at the time, you still end up with like a failure every hour to triage. That's a lot of stuff coming in. These aren't real failures, right? These are spurious failures in your test suite. So still, it's like 360 a month to deal with. So everything, when you've got this big scale testing, you just can't tolerate really any sporadic failures. A couple of war stories, sort of either customers of ours or not customers of ours that I've been speaking to. One, they decided that they had enough spurious test failures that were due to the infrastructure. They're not the code itself. They're due to NFS shares not working properly or something. And they decided their software is nice and reliable and their tests are quite deterministic. So when they get a failure, they'll rerun it up to 3 times. And as long as one of those 3 times passes, we're good, right? And as you can imagine, this very quickly led to this. You get this background radiation of failures, right? And you can't notice what is new going in, what's making it. So more and more of these non-deterministic intermittent failures went into the code base until somebody realized this probably isn't a good idea. And now they have, I think that for this case, the numbers were they're running like 500,000 tests a day, and there were sort of 500 failures every day. No, they're sort of 200 to 300 failures every day, but they're not the same 200 to 300 tests that are failing every day either, right? They're a different set, really hard problems, but they're just about recovered. So they've got a thing. They're working hard to recover that, and I think they're going to be successful in that endeavor. Another person, another company I was speaking to, was in the realm of literally millions of failures a day, right? And they're now past the event horizon of being able to do anything about this. And they're just into a world of now statistical analysis, trying to spot, which are new failures, and there's just no way back. So I've had to say to them that we can't help you. But if you're in the sort of hundreds a day, you can with enough effort get to this happy place in the top right of the chart. Right, so go green, stay green. Actually, going green is the hard bit of what I've said before, right? If you can get to the point where you have a reliable, trustworthy test suite, you will spot those failures very quickly that get added, right? You don't have that background radiation, so you can find the new bad things when they happen quickly, and you can get to the bottom of them. So going green is the really hard bit. Once you're there, you can stay there relatively easy. And I think it's essential, right? So you've got in this world that we're talking about, where your competition, the best of your competition, is going to be in the top right of that chart. They're going to be the ones they're very productive, and they've got very innovative, high velocity, good quality code coming out all the time. And if you're not there, then you die, right? So the first thing, you definitely have to get rid of the flaky tests. This is all probably not news to people in this. But even then, you've got what you get is this ever-growing backlog of flaky tests, right? And no one quite knows why they fail. And everyone kind of says, well, we'll exclude that flaky test because we're really busy this week, and next week is going to be a bit calmer once we got past this crisis and we can get back and take a look and root cause it. But of course, next week turns out to be no better than this week, always. And so the backlog just grows. So what are we going to do? Are we going to write only deterministic tests? Well, that's a good start. Let's write lots of unit tests and have them be completely deterministic. But you can't only do deterministic tests if you want to have decent coverage, right? Any concurrency in your system, any interaction with the outside world that your system has, if you're writing just deterministic tests, then you're not going to test those cases, right? Even if you can vet fuzz testing and everything else. So we're going to remove the flaky tests, like we said, but you do need to do that, but you need to be really careful to what degree you do it, right? And you can't just remove the flaky tests, because the flaky tests are the interesting ones often, right? Like often they are like that company I was talking about before, the infrastructure problems or the bug in the test itself. But sometimes they're not. Sometimes it's a real bug in the product, and it's tomorrow's outage or security breach or whatever waiting. So it's the ticking time bomb waiting to go off, right? So you've got to be careful, but to just sort of blanket excluding all the flaky tests. So we've got to fix the flaky tests, right? And yeah, but ultimately you do. If you want to get the benefits, the productivity and quality benefits of CI, got to fix those flaky tests. So we need more efficient, more effective ways to do that. So let me show you on a way that we can do that. So I'm going to come behind the lectern while we do a bit of presenting. So here is a super simple Jenkins pipeline, just some demos, right? Some demo failing tests. And in our CI, we get a bunch of artifacts that go along with our failures, right? So we'll just let this do its thing. So you get some logs, some log files. You might get some core files if you're lucky. We've instrumented that. We've changed this Jenkins so that when a test fails, we get what we call a recording, right? This is an undo recording. So I can load that up into the debugger. Now this is kind of like a core file, except it's got historical information as well, right? So I get into the debugger here. Now I'm going to switch to a slightly more user-friendly or presentation-friendly view of that anyway inside the Sea Lion product. So this is the test case that we just looked at. This is a recording of the test case. This isn't a live program, but it's in some sort of crashed state. I can see here it's in the C library. It's not in my own code. It's in machine code. We've recorded all the way into that. That's no problem. What I'm going to do is reverse step, so we go back to our call site. Now this is like going one stack frame up in the debugger, which is a fairly common, sensible thing to do. But this is a bit different because what we're doing is not going up the call stack, but we're really unwinding state. All the globals, everything go back to where we were. It's no longer a guess based on what's in the registers and what's in the stack. It's really unwound. Now I've gone back into my code, right? The code where I do have debug information for it. This is a bit of C code, just to make a simple kind of demo. So what's going on? Well, I can see now from this stack frame, I've called my cache calculate function, passed in an argument of number, and it's returned square root cache. Now it's supposed to return the square root of what we pass in, but I can see here I've passed in 255, and it's returned 0, right? And what it should have returned, 0 obviously is not the square root of 255. What it should have returned is 15, and so hence we've gone into assert 0, right? So the question is, why did that happen? Why did my cache calculate function return what it did? Well, now I'm going to do something that's kind of a little bit like magic. Well, I'm going to start stepping back through the code, so I don't have to guess where I've been. I can really go. So far, this debug experience is not that different if you're just debugging a core file or any kind of crash dump. You can kind of do what I've just done, but this is where things get really different. So I'm going to step back here, and we've gone back a line. And all my variables and everything unwind to what they were before. I go back once more. So now I've gone back to just after that function returned. And if I hit this button here, this is going to reverse step into. So it's going to go into that function, and I can see why it returned what it did. And I can see, okay, it's returning from that cache. I, in this case, is 71. You can see that the last time I ran this demo, it was 89. So I here is 71. So I'm returning the 71st item in the cache. Now, it looks like that contains garbage. So what do we say? I is 71. So if I look at the 71st element in the cache, sure enough, it's telling me that square root of 255 is 0. So this is, you know, every programmer's worst nightmare bug, right? The cache contains corrupted data, and I've got no idea how that came to be. I don't know whether is that a logic error, is it a threading error, is it a pointer problem? All I know is my cache contains garbage, and I've got no idea how that came to be. Well, what I'm going to do here now is super cool, is I'm going to add a watch point, right? So watch point, if anyone's used a watch point, allows you to watch the data in the debugger and run it until the data changes. I'm going to run backwards until the data changes, right? So that's inside this recording. It's going to take me back in time to the line of code that last modified that data, right? And I'm pulling this like, how did that happen? Who's responsible for that? So here we go. All right, so I've gone back in time to when the cache contained good data. The square root of 50 with integers is 7. Actually, I'm going to step forwards now. So this is kind of like action replay on the sports. If you watch the variables here, here's my cache here. If you watch these as I step forwards a couple of lines, step, step, that's it. That's the corruption happening right there. So I've caught it in the act. So let's just go back again. Let's just see. So what's going on? We're writing operand adjacent and square root into the cache. Operand adjacent is -1. So square root adjacent is garbage because you can't take the square root of -1. Well, the question becomes just again, well, how did that happen, right? And that's what debugging is. It's a sort of repeated sort of process of asking, well, how that happened. Well, actually, at this point, actually, I could kind of go with code inspection, but this is a demo, so let's just keep doing it. So I'm going to add another watch point to that -1, and I'm going to run backwards, and okay, it's being set here. Operand adjacent is being set to operand -1, and operand, I can see down the bottom here, is 0. So here's my bug. Called the function with an operand of 0. It returned the right thing. It returned the square root of 0, which is 0. But as a side effect, it left one entry in my cache in a bad state. I didn't notice until sometime later. So that's a bit of C code. Now what I'm going to do now is something I would advise anybody against, which is to show you what this looks like in Java. So we've come from the kind of native space, C, C++, Go, and we've got a Java product that we've been working on for a little while now, and it's just about to go into alpha. So this is pre-alpha code that I'm going to demo in front of a live audience. So let's see how we go. Right, so here's some Java code. This is in IntelliJ. Now, if you'll notice in these examples, I'm debugging from the end. That's what you do with this. You take it to the crash point and you go back. So what's going on here? Well, I'm in this DOM parser thing. This isn't my code. I'm just like in the previous example. I'm kind of in some library code, and I can't quite know what all that means. But all I do know is the program is ended by throwing an exception. So the same kind of thing, right? I'm gonna go back to the call site of that function, see if I can see what's going on. Okay, well that's still in some system code, so let's go back again. Okay, this is my code. This is the code. Well, I didn't write, but that is in my project. What's going on here? So this has thrown an exception. This line 41, and it seems it didn't like this source thing, which comes from file reader. So let's have a look at the file reader object, and that's got the file reader has inside it this byte buffer. And okay, so now I can see my byte buffer is populated with stuff that looks kind of like ASCII, doesn't it? Let's have a look. So if I go to here, so what did we say that first one was? 116. So 116 is, decimal 116 is a T. I happen to know that 32 is a space, and there's another T. So this just looks like regular ASCII, which is fine, except it's supposed to be XML. And so it's supposed to start with an open angle bracket, right? Or something like that. You know, open angle bracket is here somewhere. What's that? There we go. It's supposed to be 60, but it's definitely not that. So it looks like it's not sensible XML. So I need to find out how that's happened. Well, let's go back a line. see if, I'm going to keep watching the data as I go back here. So let's go back a line. Okay, so that all looks fine. That looks fine. That looks fine. Okay, let's go back again. Oh, yeah, now here my buffer's uninitialized. Now that's kind of interesting, right? So line 36 looks like these things if the file exists and if I can read it and if it's UTF-8 encoding. It's kind of surprising that that has side effects, right? I would expect, all those functions. Let's go forward again, just make sure that I saw what I thought I saw. Yeah, look, it's definitely filling the data. So now I'm going to reverse step into. Now, when I reverse step into, I'm going to go into the UTF-8. It has encoding UTF-8 function, right? Because that's the last thing that happened. We'd evaluate left to right. The most recent thing to happen was that function. So reverse step into that function. Okay, so let's just check that's the reverse step. And okay, so it's working on this reader thing. Now let's have a look. That's the file reader again. So let's just have a look at its byte buffer. See what we have. Okay, so it's still in the bad state here. Go back one line. I'm really homing in on it now, right? So that's where it's been set. Let's just make sure again that I saw what I thought I saw. So if I go forward, yeah, that's it. All right, so what's going on here? So this line 26 is changing state in a way that I wasn't expecting it to. Well, it's a new buffer reader from reader, and it's doing a read line, right, which is going to read into that file, see if it does contain the UTF-8 encoding, and then it throws away the buffer. So that's the side effect, right? It read into that buffer, had a side effect, wasn't expecting it to. This is based on a real bug that someone was looking at for many weeks recently in a different project. Exactly this kind of unintended kind of side effect thing. So that concludes the live demo of pre-alpha code. Hooray! And now let's go back to our presentation. Right, so let's come back to what we were saying. So this is intermittent tests that we have to fix. And this technique, what I've showed you, by the way, it's just useful for debugging intermittent difficult failures in general, not just inside CI, but that's the context that we're talking in today. And so with these thousands and thousands of tests all the time, even a very tiny error rate is really bad news, right? So yeah, as I said before, we'll come back and fix them next week, but that's not going to happen. So rather than this kind of world where we try and do all the circumstances that might have possibly or maybe not were required to affect our bug, the point is let's record the execution. I'm going to give you, that's all very theoretical, little toy demos. Let me give you, an obvious question is, well, how does this scale to real-world complex codes? I'm going to give you a real-world example. How are we doing for time? No, we're all right. We've got plenty of time. So SAP HANA, right? So HANA is the sort of core in-memory database made by SAP. It's millions of lines of highly optimized C++ code. It has very high reliability requirements. As you might imagine, it's a database that sits under, whenever you book an airline ticket or the scanner goes beep at the supermarket or whatever, it's probably an SAP system sitting under that. So as you can imagine, as you'd expect, as you'd hope, they have sophisticated and extensive testing infrastructure. One of their big things is a thing they call PMUT, Parallel Multi-User Testing. And this is just a whole bunch of clients, hundreds of clients, hammering away on the database, doing random, joins and select and everything else, trying to just push the database into these weird kind of, one in a bazillion corner sort of states, corner cases that they wouldn't normally see. And this is like, this kind of works, right, in that it will push the database into bad states from time to time, but basically in a way that's impossible to debug, right? The SAP engineers will come in the morning and they'll be, yeah, that thing, we got that crash again at 3 a.m. on Sunday morning. It's like, what led to that? So that's when they started doing the recording, the live recording that we were talking about. Exactly what we've just seen. I'm going to step through. I think I've got a horrible slide version of the demo that we just saw, just in case I was feeling cowardly, but I wasn't. Fortune favors the brave. So yeah, so SAP integrated live recorder into that PMUT system, meaning that when they get those, really difficult sporadic failures, it spits out a recording, and now the engineers can look at that and they can go straight to the root cause, right? So diagnosed, these are real SAP HANA bugs caught with PMUT and diagnosed with live recorder. So memory leaks, another memory corruption defects were caught. Issues in the networking code, right? So you notice this is something where we're interacting with the outside world. It is often difficult, the network API, one of the packet send fails or something, occasionally, or there's some buffer overflow internally or something. Race conditions is a very common one, right? So and particularly with this, they have these big shared state data structure problems. Garbage collector issues, and my favorite, because it's just such a real visceral kind of example, is a race condition in the caching logic, which meant that one access in a bazillion, the wrong row from the database was returned. Right? And if you think about what this means, and this is somebody else's bank details or medical records or something, right? This is really serious. In fact, it's the sort of thing that if it happened in production, 99 times out of 100, the user would go, what? That doesn't make sense. Refresh. Okay, now we're good, right? But one time in 100, somebody might go, oh, that looks interesting. So they were able to capture all of these issues inside their testing, but with that live recorder, very, very difficult. They're not really actionable, right? Those parallel multi-user test failures. With live recorder, they can fix them all before they ship the product, right? And they can keep their test suite green. So that's me. If you want any more, you can obviously follow me on Twitter. If you're interested in the GDB, which is obviously C++ debugging, at least mainly, I have a little series, GDB Watchpoint, which is just sort of 5-minute videos that talks about what we're doing. But that's the overview of what we've just seen. Do we have any questions on any of this? Or was it all super clear?
What are the current languages that you guys support?
So we kind of come from the native space, so C, C++, Go, Fortran, stuff like that. The Java you just saw the demo of. So I should if I'll just step back a bit. So the technology itself is kind of language agnostic. It's quite tightly close to Linux, I should say. This is about Linux runtime systems, but there are kind of equivalents or similar systems for Windows. And it's capturing a Linux process execution and then allowing you to rewind, replay that down to the instruction level. What you have to do to be useful is translate it back to a view that the programmer can understand, right? So when you typically, not always, but typically that means in a debugger kind of view, and that means that you need to interface onto that. So that's why I showed the first version is C, we've got C++, Go, as I said. Java's more tricky because it's just harder to go from a program state to process state, bits and bytes in memory and registers, to where you are in the Java program. So that's kind of kept us busy for the last sort of year or so as we kind of worked around a couple of tricky issues there. I mean, particularly because the thing that caught us out with Java, the thing that proved to be a pain, is that the Java is designed to have lots of debugger. There's this JDWP. You can make your own debuggers, and it's all kind of designed for that. But they made an assumption that sounds like a totally reasonable assumption. That is, you put breakpoints on lines of code before those lines of code are executed. It's not unreasonable that the Java designers decided that's an assumption they would make. And so what they mean by that is when you put a breakpoint on a method, that method will always be run in interpretive mode, not JIT compiled. And for us, that's a problem, because for us, you run the code before you know where the breakpoints are going to be. So we had to kind of work around some of those type issues, but that we've done, as you've saw in the demo. So a long answer to the question, but really mostly our customers are C, C++, Go, and soon Java and other Java-like languages. And one by one, we'll do more and more.
Do you have similar problems with Go that you had with Java?
No, because Go sort of compiles down to machine code, right? So you can map back from the Go, from a process state, from a core file, if you like, to to Go. I was going to say Goland, but that's confusing because it's a term of another product. But but into sort of the Go space. So we do integrate with the Goland IDE, by the way. But yeah, so Go was much easier for us to do technically. It's a much thinner layer to go from actually what the bits and bytes of the machine are to what the programmer model is.
In the presentation, so I'm kind of interested in how this would go. The presentation would be my Go structures and my Go routine was the underlying.
Mm-hmm. Okay. Absolutely, yeah. So if you've used the Delve debugger and Goland and all that, so it fits in. In fact, we fit in with that. So we don't try to replace the debuggers. What we're providing is this, this time machine, if you like, so we can rewind time to a given point, and then we present that through an existing debugger. So the debuggers you saw in the demo, or Delve or whatever. So we're not trying to replace any of those. So yeah, so you can, and that's in in production right now. So yeah, so the Go routines make life kind of interesting from that point. But that's what Delve was designed to make better, right? Is the working with the Go routines, but right. But for us, we sort of don't care. That all happens at a different place. That all sort of happens at layers in the stack above us, if you like.
What kind of storage backends? Or?
Yeah. So the storage, we're just writing to a file, right? So it might be network mounted or whatever, but we just need a file on the local file system that you can write to. The storage requirements are much less than you might expect, because if you think kind of what this is doing, right? Then we can literally go back to any instruction that executed and see the full program state. Well, clearly you can't store the full program state at every instruction. That would just be crazy. But even if you were to say, well, I'm just going to store the delta of each instruction that executes is going to change, I mean, if the instruction doesn't change at least something, then you're in an infinite loop, right? So it's got to change something. But typically it will just be one location in memory and maybe some registers and some flags. So perhaps 1632 bytes per instruction, billions of instructions every second. Suddenly that gets to be huge amounts of storage and go very slowly. So what we do is in fact, we don't store everything. We store just enough to allow ourselves to recompute prior states. So in the demo, when I go back one line, what we're doing is going back to a snapshot and replaying that forward and stopping just where you need to be. But the trick, of course, is that we have to make sure when we do that we replay exactly what happened the first time around. Because these sporadic, 1 in a bazillion failures, if you just run the program again, they do different things. That's why they're intermittent. So what we're doing is capturing the non-deterministic stimuli to the program that will cause it to take a different path. And on a Linux system, that actually comes down to the following things. Any system call, right? Because if you think about it, right, if the program could recompute the answer just from its internal state, why would you make it a system call? It would be a library. But it's so, any network or any file access, but, get PID or get time of day, that's all of those we capture. We need to capture any thread switches and thread interactions and all those kind of timing things, and also asynchronous signals that might come in, SIG alarm or something. Some instructions are non-deterministic. Most instructions are deterministic. Add two numbers together, you better get the same result. Others, like RDTSC or the modern Intel processors, have a get me a random number instruction. Those are non-deterministic kind of by definition. Others, you can tell if you read the Intel manuals in enough depth, I hope you never have to, that the designers decided it would be cheaper to change the manual than fix the silicon when different generations of the chip come out. So they've said, well, actually, maybe sometimes we leave this unspecified as to which flag will be set. And shared memory, access is to shared memory. Any memory shared with another process or shared with a system, so it's kind of doing asynchronous I/O to it. And so we capture all of those. We capture them into our event log, and then when we're replaying, we just pull those out of our event log rather than actually accessing the network or whatever it was it did. And so the resulting, I mean, it depends what your application, so it depends hugely what your application is doing, but typically of the order of a few megabytes per second of recording. And then it's a circular buffer, so you just say, well, I want, half a gig or whatever you think you want, and then, if it goes for long enough, the old stuff gets chucked off the back.
at all to
Nope.
take advantage of this?
No, so that was always a goal right from the beginning. So no changes to your compiler, no special libraries to link against, anything like that. You just, it actually be doing a JIT retranslation of the code as it's running, so we didn't require that. There is a library you can link against, and which if you do, you get an API and you can control, you can start, stop recording, say recording at this time, inject metadata, do whatever you want. But that's, like you don't have to do that. You don't have to link against the library if you don't want that facility.
You want to isolate to a specific module or a specific hotspot that you need, then you can bring in that
You
library.
could, although there is a pretty high overhead in actually turning the recording on and off. So we wouldn't say, oh, well, you know it's this function, this method, this area, turn it on here and off here, because if you do that too often, and also you defeat the whole thing this is built on, is that we can recompute the previous states. Sure. And if you keep turning it off and turning it on again, you defeat our ability to kind of do that. But it's also nice that you don't, the point is you don't have to as well. It's designed, it's used on regular day-to-day bugs. I always say if you can turn, we've got examples of people literally turning year-long debugging sessions into hours with this, literally. But I also say if you can repeatedly turn an afternoon debug session into 10 minutes, that's also a win that you shouldn't overlook. But the point, those things, and especially the stuff I've been talking about today, the intermittent once-in-a-blue-moon failures, the whole point is you've got no idea where they're coming from, right? So you really don't want to have to say, I think it's here. Just record the whole thing, and you get the most recent hour of execution or whatever it is, and you don't have to think about what was in and out. But you often say, well, I got different phases my program goes through, so I don't want to instrument the whole kind of load. If I'm doing some sort of load transform kind of thing, I don't want to have to record all of the loading states. So I'll just skip over that, or I'll allow. A lot of our customers have it inside their products, and then it's, so if it's a database company, you'll have some embedded SQL command that you can just turn on the recording at that point, so it can be very dynamic. But that's triggered by a human, if you like. But then, and also the metadata stuff's very cool as well. So you can inject metadata into the recording. So if it's, this transaction started now, and then or this corresponds with the log message I emit out as well, then that's quite useful. So the library is good, and most of our customers do end up linking the library in. But to get started, you don't need that. Cool. All right. Well, with that, thank you for listening intently, and well done for coming to the best talk, unlike everybody else. And thank you.